You've probably used a computer mouse for thousands of hours, and yet have you ever stopped to wonder how it works? Well, essentially the modern computer mouse is a merger of 7 different technologies and some rather ingenious engineering. It would take over an hour to cover all these technologies in depth, so in this video we're going to focus on just one, the image sensor, and find out what exactly happens when you move your mouse around on a mousepad. After that, we'll take a look at a gaming mouse and see how some mice have 25,000 dpi, or dots per inch, while others have only a few thousand. Stick around and let's jump right in. At the bottom of this mouse, we have the Image Acquisition System, or IAS, which is composed of an infrared LED, a pair of lenses, and the image pixel array. Infrared light generated by the LED passes through a lens and illuminates the surface directly underneath the computer mouse. Next, the infrared light bounces off the surface, passes through a second lens, then through a tiny aperture, and finally hits this rather sophisticated image pixel array, or image sensor, which is composed of 1,600 pixels laid out 40 by 40. This is important. Your mouse doesn't capture the color or design of the mousepad or surface. Rather, because the light is emitted at a shallow angle, it illuminates the texture, or the ridges and valleys of the surface, kind of like a sunset falling across rolling hills. The tops of the hills catch and reflect the light and are illuminated, but the light doesn't reach into the valleys, and thus they remain dark. Your eyes might see just a uniform black mousepad or wooden desk, but because of the shallow angle of the infrared light and the focus of the lenses, the image sensor is able to capture a topographically and texturally complex landscape. Note that if the surface were perfectly smooth with no imperfections, the mouse would struggle to work on it, which is the reason why some computer mice don't work well on glass. Furthermore, this image sensor, with its 1,600 pixels, focuses only on a tiny area just 1/200th the size of a penny, immediately below the mouse. However, the key is that the image sensor takes up to 17,000 pictures of the surface every single second, and thus, even if you move your mouse across the mousepad for just 1/10 of a second, the image sensor would take around 1,700 pictures during that quick move. And here's the kicker to this technology. Your mouse doesn't save any of these images, but rather, every time it takes a picture, it compares it to the previous one taken 59 microseconds earlier. The microchip then uses the difference between the two images in order to determine the change in X and change in Y, or in essence, how far and in what direction you moved your mouse in that 1/17,000th of a second, or 59 microseconds. Let's dive a little deeper into this idea. If we have two images of the topographical texture of the surface taken 59 microseconds apart, how exactly does the microchip determine the change in X and the change in Y between them? Well, to calculate this, the two images are sent to a section of the microchip called a digital signal processor, or DSP for short, where an algorithm called cross-correlation is executed. As mentioned before, each image is composed of 40 by 40 pixels, and every pixel generates a value between 0 and 4095 that relates to the intensity of light that hits that particular pixel. Here we represent the values by the height of each pixel. The digital signal processor, or DSP, takes the first image and overlays the second image on top of it. Next, the DSP subtracts all the values of the second image's individual pixels from the first, and we get a new resulting image. The processor then shifts the second image around while leaving the first stationary and continues to calculate the difference between the two images until a position is found where the resulting image is at a minimum. The amount of shift in position to reach a minimum resultant image tells us exactly how far the mouse moved between two successive images taken 1/17,000th of a second apart, yielding a value for the change in X and the change in Y, measured in pixel counts. 59 microseconds later, another image is captured, and the processor performs the same cross-correlation algorithm, but with the new image shifting around and the previous image stationary, resulting in another set of values. The processor continues to capture new images and executes the cross-correlation algorithm 17 times. It then adds up all the values, and we get how far the mouse moved in 1 millisecond. This combined change in X and change in Y for the 1 millisecond is then sent to the system on a chip over here, which in turn relays the information to your computer using either a USB transceiver or Bluetooth. And that's how your mouse calculates movement every single millisecond. Let's now take a look at the difference between gaming mice and non-gaming mice. Aside from the sharper-looking shape of the mouse, a different number and layout of buttons, and the LED lights, the first main difference is the specified DPI, or dots per inch. Gaming mice have DPI specs of 12,000 to 25,000. While non-gaming mice are closer to 850 to 4,000 DPI. But that begs the question, what exactly is DPI? Well, when you move your mouse to the right by 1 inch, however many units your cursor moves across the screen results in the value of dots per inch. A DPI of, say, 2,000 means your cursor will move 2,000 units for every 1 inch of movement of the mouse. However, how does this relate to the image sensor and the cross-correlation algorithm that we talked about earlier? Well, let's say each pixel in this 40 by 40 pixel image sensor has a length and height of 30 micrometers, totaling a square 1.2 millimeters by 1.2 millimeters. If we were to extrapolate this sensor's pixels out to 1 inch in length, then we would need around 850 pixels, which in effect would yield a DPI of 850. In order to reach higher DPI, we need to subdivide each whole or integer pixel using multiple cuts. Let's take each pixel and subdivide it by 4 along the X direction and 4 along the Y. Each pixel turns into 25 subpixels, and now our 850 DPI sensor has a DPI of 4,250. However, if we were to make 29 cuts along each length of every single pixel, we get a DPI closer to 25,500. Note that DPI is a linear unit, whereas pixels per square inch is a square unit. So now that we have the general idea, how specifically does it happen? Well, a common technique for subdividing whole pixels into subpixels is called interpolation, and the simple version goes like this. Here we have 4 whole or integer pixels, each with a value for the intensity of light hitting that pixel, and just as before, the height of each pixel represents the value as well as an approximation for the textural topography of the surface. Next, we draw a line between the tops of the 2 sets of pixels in the X direction, and then draw lines between the 2 lines in the Y direction. Then, depending on how many subpixels we want, we subdivide the lines accordingly. At each intersection, we have a corresponding value for a new interpolated subpixel. So when you change the DPI settings of your mouse, what you are actually changing is the number of subdivisions in this interpolation algorithm. Here we're showing a bilinear interpolation. It's called bilinear because we draw straight lines between the whole integer pixels. However, a bicubic interpolation, which uses a little more math, can be used to create a smoother topography. One additional difference between gaming mice and non-gaming mice is that gaming mice typically report their movements to the computer 1,000 times a second, or once every millisecond, whereas non-gaming mice send data 120 times a second. Furthermore, the number of pictures taken every second, called the frame rate, of 17,000 is only this high when you are quickly moving your mouse, and it scales down when your mouse is stationary in order to conserve battery life. One important thing to note is that there are a wide variety of mice out there, and in this video we listed specs of a frame rate of 17,000 and a resolution of 25,000 DPI, which are the specs for a rather high-end gaming mouse. Specs typically range from 4,000 frames per second to 17,000, 1000 dpi to 25,000, 18 by 18 pixels to 40 by 40, and a reporting rate from 100 to 1000. Furthermore, we showed a mouse that uses an infrared LED for illumination, whereas some mice use a laser, older mice use a red LED, and prehistoric mice use a ball. Note that at the beginning of this video we said there were 7 different technologies inside this computer mouse, and thus far we've only covered 1. The next video we're considering making is on the scroll wheel and how fast we can get this wheel spinning. If we can get this current video to over 30,000 likes, we'll be sure to make that video. Inside this mouse is a rather complicated printed circuit board, or PCB, and without it there would be a rather messy jumble of wires that most likely wouldn't even work properly. If you want to make your own devices, you're going to have to create your own PCB, which is rather fitting because this video was made possible by our sponsor, PCBWay. PCBWay can quickly manufacture your PCBs with competitive prices and impeccable standards. They also provide PCB assembly services where they populate and solder the components to the PCB. Check them out using the link in the description below. We believe the future will require a strong emphasis on engineering education, and we're thankful to all of our Patreon and YouTube membership sponsors for supporting this dream. If you want to support us on YouTube memberships or Patreon, you can find the links in the description. Also, thank you to Logitech for providing information, reviewing the script, and providing a mouse to tear apart. Also, remember to subscribe, comment below, and share this video with others. This is Branch Education. Thanks for watching to the end.